So, ladies and gentlemen, I'm happy to speak to you today. My name is Vladimír Macko, and I will be speaking to you about LLMs. So, if you have not noticed, we are currently living in the age of large language models. And in recent years, we received a whole zoo of AI tools like ChatGPT, Claude, or Grok. I guess most of you used at least one of them. But what is most important, we also received the open source and open weight alternatives like Llama 4 and DeepSeek. However, when you look at the frontier models, you will find out that all of the best ones are either behind closed APIs, or they have hundreds of billions of parameters that require hundreds of gigabytes of GPU memory. For interest, one model that recently claims to achieve context size of 10 million tokens requires a meager 512 GPUs that we all have at home. This is Jeff Dean. This is the head of AI at Google Research. And Jeff wonders why it's hard to run these models on consumer GPU hardware. I mean, we don't need to wonder, but we cannot expect any or much help from the big players, big corporations, so we need to help ourselves. And that's one of the reasons for this research. So my name is Vladimír Macko. I have background in research. I spent some time in Google AI research in New York. I did privacy-preserving authentication, then some NLP, and I'm currently doing an external PhD here at Comenius University. But most importantly, I want to run those LLMs on a single GPU. So, what is LLM? Let's take a look at a sample architecture called Llama 270B. And we see that, this is it. There's not that much to it. We start with an embedding layer, which is pretty much a linear layer anyways. Then we have a few linear layers, and then we end up with another linear layer. And for succinctness, I have skipped some things related to embeddings, activations, and normalization. However, this is the network in terms of the parameters that the network has. Together, the network has 70 billion floating point 16 parameters, which means 2 bytes per parameter. That is 140 gigabytes of disk space, and 99% of these parameters is used for matrix multiplication. If you want to run this, you need 2 H100 GPUs or equivalent, which costs $50,000 to buy or $3,000 per month to rent. And if your grant allows for this, well, let me know. What is much more available, even though still this is like a luxury hardware, is NVIDIA RTX 5090, which is expensive but reasonable consumer GPU that you can get, or you can get soon. But let's look in the inside. What is inside the GPU, what it actually is. So the computation on GPU is done by 170 SMs, or streaming multiprocessors. You can imagine it as cores of CPU, but I will get to details slightly later. These SMs are connected to L2 cache that is relatively small and has only 69 megabytes. That L2 cache is connected to global memory, which is much larger and has 32 gigabytes. And the whole thing, and the whole GPU, is connected to the host memory, which means to the machine, that can have whatever memory we want. Important part here is that the data transfer speed between host memory and global memory is 3 times slower than between the global memory and SM, which means that it takes 4 times longer to read and compute something from host memory than from global memory. And to a large extent, this is, in a way, the main driver of this research. That if we want to run fast machine learning inference, we pretty much need to fit the whole model into the global memory to avoid the host transfer, which is very slow. Okay, so how do we fit the model there? To fit it there into those 32 gigabytes, we need to make it smaller. Again, let's have a look at what the model actually is. At the top, we have the input vector. Then we have a matrix representing Q, K, V, and O projections. Then we apply something called attention layer. And then again, we have a matrix that's representing gated NLP, or multi-layer perceptron. We take this block, apply it 80 times, and finally we get the output vector and the output predictions of the model. There are two very common techniques on how to make the model smaller. One of them is called quantization. And what we do there is we take the representation of the model and represent the weights in lower precision. You can imagine it as rounding down floating point number, give or take. And we can comfortably go from floating point 16 to FP8 or int8 or even int4. Second important technique is distillation or retraining. There we take the architecture of the model and we downscale its parameters. So instead of having 8,000 hidden dimension with size 8,000, we have 5,000. And instead of repeating the block 80 times, we do it 40 times. The metric that we are measuring and that we are interested in is something called perplexity, which tells somehow how good how good is the idea of the world encoded into the model. Let's give it a take. We explain it a bit more further. But what we see is that with quantization, we can go down to 4-bit and get a model that has 35 gigabytes with very minimal degradation in perplexity. Low perplexity is better, higher is worse. However, this is still not good enough. We cannot fit that 35 gigabytes into those 32 gigabytes, so we need to do something else. On the other hand, we have distillation. And thankfully, Meta provided us gracefully with other variants of the Llama 2 model, with Llama 7b and Llama 13b. And those can fit into those 32 gigabytes of GPU memory. However, their perplexity is much, much worse. And we cannot count on this. Like if somebody else releases a different model, we cannot count on the fact that they will release smaller distilled versions as well. And also, we do not want to do the distillation ourselves because training or retraining a smaller model has similar costs to training a large one, or it's at least in a similar orders of magnitude. So we need something kind of in between. We need to somehow get rid of the unimportant parts of the model, but how to do it? If we are going to modify the trained model, we need to be very careful about something called superweights. Superweights is a phenomena in trained LLMs, which tells us that in the large model, there exists a very small set of extremely important weights that are fundamental to the functioning of the model. And if we take those weights and set them to 0, or modify them in poor way, the model completely breaks. So let's illustrate. We take a Mistral 7b model, and we ask it to complete a sentence language modeling is. And the model happily completes it. It's the most fundamental and basic task in machine learning and neural language processing NLP. I mean, a bit opinionated, but sure, sounds good enough. Then we add this single line of code, which accesses specific weight out of those 7 billion and set it to 0, and the model completely breaks. So all of a sudden, language modeling is not like a not as good / without is that for not whatever. So we need to be very careful about this. And there are two ways how to mitigate it. A, we either need to check that we are not removing the superweights, or B, if we are removing something, we want to make sure that we are adjusting the rest of the network in a proper way that is somehow optimal, that can compensate for this. So the work that we are doing is mainly based on the previous research done by my advisor, Vladimír. There he is. And it's based on a method called pruning. So what we want to do is we want to take the weight matrix representing the parameters of the model, and remove a large part of them away, either by setting them to 0 or actually removing them, making the matrix sparse, reducing the memory footprint of the model, and maybe even making it faster. This work is also very connected with a different previous paper called Simple and Effective Pruning Approaches for a Large Language Model, which gave a way how to easily achieve at least the base state of the pruning, or how to get a decent initial solution for pruning of the network. Now, if you don't like math, and maybe there are people like that here, close your eyes. I will tell you when to open them. So how does this work? To make this problem more tractable, Vladimír separated that into a set of layer-wise problems and treated each pruning of each layer to some extent separately. And it turns out that if you do it for one layer and you fix the matrix, you fix the sparsity structure, this problem turns into a convex problem, and you can apply convex optimization, in this case, ADMM optimizer. This optimizer gives you an update rule on how to, given the sparsity matrix, how to update the weights to get actually not certified, guaranteed convergence for that particular step. You update the weights, and then you use the previous paper, Vanda, to adjust the sparsity mask. And you iterate this until you're happy with your model, or you reach the desired level of sparsity. If you close your eyes now, you can open them. And the question is, how well does this work? So at this table, we have some results. On the left, we see different levels of sparsity, so how much stuff we removed from the network. And on the top, we see the different sizes of the models, so llama 7b, 13b, and 70b. And we are looking at perplexity on the Wikitext dataset. To maybe explain a bit more what is perplexity, the model gets some tokens on the input, and then outputs a probability distribution over the vocabulary on what it thinks should be the next token. And what we can do is we can actually, if we know what is the next token, we can compute how perplexed or surprised the model was that it's seen another token. We accumulate this surprise and we get these numbers. And lower perplexity means that we have a better model because it's less surprised by the real world. So what we see here, this method turns out to be a best pruning method compared to the other baselines and compared to the state of the art at the time. And we see that we can take a model like 70b and prune it down to 50% with some perplexity degradation. Unfortunately, it is still better to take a distilled version of the model and take a smaller alternative that was trained by somebody else than to take a larger one and prune it down. So for example, if you look at the 13b 50%, we prune the model pretty much the size of 7b, but it's unfortunately better to use 7b than to use 13b pruned version. Yeah, so this is a good pruning technique, but unfortunately, it's still better to use distillation. Like another data set or another way how to evaluate LLMs, is zero-shot accuracy on various tasks. In this case, you see the data sets on the top, and here are the numbers for llama 7b across various densities and across various other baselines. And we see that in aggregate, the ADMM method works the best. However, there are some cases for various data sets where it is beaten by other baselines. For curiosity, what you can expect is that if you take a large language model and you remove 50% of the model away, you can expect like 5% degradation in zero-shot accuracy on these question answering tasks. If you go down to 60%, you can expect like 7% degradation. 70%, it starts to be a bit more noticeable, 15%. And for 80% sparsity, you are pretty much cut in half. Okay, how can we push this further? Or how was this pushed further? What if instead of having one weight matrix, you have two sparse matrices? And you are trying to reconstruct the original weight matrix as a product of two very sparse matrices. But again, you need to be careful that you don't introduce actually more parameters than you had before. And this is exactly what Vladimír Boža did. In the paper, two sparse matrices are better than one, sparsifying neural networks with double sparse factorization. Again, if you don't like math, close your eyes, but this will be much more gentle. So what do we want to do now? is we want to take the original parameter matrix W and find two matrices A and B whose product is as close to W as possible and whose number of non-zero elements is kept by some constant Z or our desired sparsity. Again, it turns out that if you fix one of the matrices, A, for example, you can use or to a large extent, you can use the work done in previous paper by Vladimír to optimize the matrix B. So we fix A, optimize B, fix B, optimize A, and so on until we reach desired properties of the matrices and good enough model. Good. And I'm happy to say that we just returned 2 weeks ago, 1 week ago, who knows, from Singapore, that we presented this work at ICLR or iClear 2025 in front of 8,000 to 10,000 people, I guess, something like that. 6,000 to 8,000 people in front of a lot of people. If you're interested, the poster will be in somewhere. We have not decided on the place yet, I guess. Yeah, the poster is very huge, but it was nice. By the way, kudos for Comenius University for nice colors in the templates. Okay, but how does this work, or how well it performs? Again, we are looking at the Wikitext perplexity, or perplexity on the Wikitext dataset. And again, we see that like all the lowest numbers are in bold and all the bold numbers are in the double sparse factorization column. However, to highlight some important results, it turns out that using this method, you can take a model like Llama 213b, prune it down to 50%, and you will get a better perplexity than equivalently sized Llama 27b, which to our knowledge is like one of the first papers that achieve something like this. And you can push it even further, and you can take Llama 70b, prune it down by 70%, which is quite odd, and you will get a model that is roughly 21 billion parameters long, so large, so bigger than Llama 213b, but the perplexity is very similar, so getting there. And yeah, so this turned out to be much better than distillation. Important enough, these results translate to other modalities as well, because nowhere in the talk not much of the method is dependent on the fact that we are working with LLMs, but we are working with matrix factorization. And it turns out that you can do something similar for image classification as well. So if you look at test accuracy on ImageNet using ResNet 50 as a baseline, we see that we can take all the way to 90% of the parameters of the model, throw them away, and only go from 76% accuracy to 74%, which is quite surprising, and it shows that some of the models are pretty bloated in a way. So as a takeaway, it turns out that you can take a model, reduce its size down to 10% of the original, and only have 1.6% drop in accuracy, which can be very, very useful for some applications. However, back to Llama 70b, it turns out that the best results can be achieved with combining pruning and quantization. So we can take Llama 270b, that has 140 gigabytes and perplexity 3.12, apply double sparse factorization and 4-bit quantization, which takes around 4 hours on 4 A100 GPUs, which, if you are interested, costs like $20 if you want to run them. And we arrived to a model called pruned Llama 270b that only has 26 gigabytes of memory and perplexity 3.76, which there is some degradation. However, compared to the baseline of distilled model, Llama 213b, that has perplexity 4.57, so that means that we are much, much better. So overall, this method can reduce the size of the model by staggering 81%. However, it increases the perplexity from 3.12 to 3.76, which may be completely fine for some applications. Okay, we saved some disk space and some memory, but does it matter? And can we push it further? How does it, for example, relate to speed of the inference or of the model? So let's take for this, we need to dive a bit deeper and again, learn something more about GPUs and how they work. So GPUs perform two tasks. They move memory around and they perform computation. And these two tasks are specified by two attributes, which is memory bandwidth, how many bytes per second can the GPU access or move around. And second is performance, or how many flops per second can the GPU perform. And if you take the ratio of these two numbers, you will get a quantity called ops per bytes, which tells you how many operations can the GPU perform in the same time as it accesses 1 byte of memory. That looks kind of arbitrary, but we'll see how it's used. Important part is that you can compute the same thing for the algorithm that you want to run on the GPU. So how many bytes the algorithm requires and how many operations the algorithm requires. So for example, if we are interested in LLM FP16 inference, which is pretty much matrix multiplication with batch size 1. And it turns out that this algorithm only requires 1 operation per accessed byte of memory. That means that this algorithm is always memory bounded, which means that it's limited by the speed of the memory, not by the speed of the processor. And that means that if you want to make it faster, few operations will not make the algorithm faster, but having it access less memory will make it faster. And that's the reason why we are interested in pruning. Because in pruning, we are exactly doing this. We are reducing the memory that the algorithm needs to access. Okay, and how does it work in practice? Or how do we actually perform sparse matrix multiplication in practice with the model? So again, here's the diagram of the GPU. Now we are able to fit the whole model in the global memory. So we got rid of the communication with host memory. And the question is how to actually perform the matrix multiplication. It turns out that the easiest way to do it is to just reconstruct the dense matrix on the fly. And because we are still in global memory, we don't need to communicate with the host. And because we are memory bound, not compute bound, the set of additional operations actually doesn't matter that much. So we already made it faster because of this, because we removed the need for communication with the host. However, can we push it further? Could we also decrease the communication between the cache and global memory and make this algorithm even faster by actually implementing fast sparse matrix multiplication? So again, we need to go deeper. And I'm probably reaching the 25th minute part of the talk, so I will not, I will understand if you'll douse off now. So just head up for that. So let's understand how sparse matrices are actually represented and how can we work with them. So this is a sparse matrix, actually represented as a dense matrix in the dense format of FP16, R rows, C columns. This representation takes 128 bytes of memory. And that's our baseline that we want to somehow use or beat. One very common sparse matrix formats is something called CSC, or compressed sparse columns. I know it's a lot of numbers. But what we do in this format is that we store an array of non-zero values, the orange ones. We store row indices of each of those non-zero values. And we order these values by the column in which they are. And we also store how many numbers or how many non-zero values are in each columns. And we store it as cumulative sum for technical reasons. Unfortunately, if we count how much memory we are using, we'll arrive to a number of 210 bytes, which is much worse than the dense representation. So it turns out that this very widely used format is very impractical to limit to almost unusable for the sparsities that we are interested in. And this problem becomes even worse if you would like to use weights that are in some quantized formats, because then the indices will take up much more space than the actual important stuff that we have in the matrix. Luckily, there are some alternatives. And one of such alternatives is something called NVIDIA 2-4 sparsity, which is a structured sparsity. And what it says is that if we can guarantee that every 4 elements of our matrix will have at most 2 non-zeros, we can have a very succinct representation of the sparse matrix. We just remember the elements, and for every group of 4, we remember a bitmap of where the element actually is. This gives us a very, very good storage requirement, which is 68 bytes. However, it has minimal flexibility because we cannot use different sparsities, only 50%. Well, we can, but we will not save anything. And yeah, that's pretty much it. And the structure of the matrix is very restrictive. So it turns out it can be very hard to come to an optimization algorithm that prunes the model in this way. However, it has good support, and NVIDIA actually has GPU multiplication kernels for this specific format. But what we can do is that we can take an inspiration from this format and make it more general. So instead of enforcing the do-for sparsity, we take the matrix, we store the array of non-zero values, and we also store a bit mask of whether some element is there or is not there. You can see that it can be reconstructed back if we have a reasonable ordering of the values. And also this has the same storage requirements as the 2-4 sparsity, so only using 68 bits, which, because we have 50% sparsity, is very close to the optimal that we could get. And most importantly, this is very flexible. However, there is no support for it. And even though this format looks like some kind of initial idea that you could go for, well, there are no kernels for it. So there is nobody ever implemented a fast matrix multiplication for this. So how hard can it be to write a matrix multiplication algorithm? I mean, it's like 3-4 loops, so what could be the problem? Here is a representation of what a naive implementation of matrix multiplication in CUDA looks like. So it really is like 2 for loops and then some parallelism around it. Beautiful, 10 lines of code. Well, the problem is that it's 100 times slower than the reference implementation that you have in libraries like cuBLAS. Unfortunately, cuBLAS is not open sourced, so we don't know what's inside, and we cannot just take it, copy-paste it, and change it. And the best public implementation that are available is done by this lovely gentleman, which achieves only 95% of speed of the cuBLAS that is closed-sourced. Alternative that we tried was to implement the matrix multiplication for other use case in a language called Triton, which is a high-level GPU programming language. If you ever would like to write some GPU code, you should consider using this as a starting point. It's easy to write. Again, the code doesn't look that horrible. I mean, it does, but it's not a lot of it. It's pretty much a Python. This achieves 90% of the speed of cuBLAS. However, it's extremely hard to improve, and we have not found a way to make this work with sparsity properly, or not to work with sparsity in a speed up that we would like to see. So I still have some time, so we can go a bit deeper, and I hope I will lose everybody in the audience. So let's go. This is how the 96% implementation in terms of speed roughly looks like for the GPUs. So we have the matrices A and B. We have the dimension K over which we are multiplying and summing. And first, we need to split every one of those matrices into blocks of size Bm times Bk and Bv times Bk. And each block will produce a part of the output. So in the output C, there is like one square, and some set of processors will be responsible for computing this square. However, inside that block, for reasons that are related to memory coalescing in GPUs and fast access to different parts of the memory, we also need to split this specific block in a very particular way across the processors that we have on the streaming multiprocessors, or called VARPs. Then each processor on the GPU needs to go through its own ordering of the elements to avoid some conflict in the memory. And finally, each of those processors in every read needs to use vector operations to make memory loading fast. Let's put it that way. And hooray, we have arrived into 96% implementation. Good. So what does it do with speed, or what do we know about how this actually influences speed? If you take dense matrix multiplication from GPU memory as a baseline in terms of flops, and compare it to the same dense matrix multiplication, but if you need to load the matrix from host, the host one is only 0.3 of speed of the dense one. So this is the reason why we really want to have the model inside our GPU memory. If we look at a matrix with density 30%, the theoretical optimal that we could ever hope to achieve is something around 2.75x speedup compared to dense matmul. And thanks to collaboration with Elvir Crnčević from Institute Science Technology Austria, ISTA, we currently have an implementation that achieves roughly 1.4 to 1.8 x speedup compared to the dense matrix multiplication. And where we would like to get, and hopefully we'll get pretty soon, is something around 2.4x speedup for the same density. Okay, do I still have some time, or? Okay, so I will to lighten the mood a little bit, I will show some like side implications of this research that have like very nice practical applications. So this is a weight matrix in 8 bits integers. So we have a bunch of 8-bit numbers. And I want to show you how does it look when we perform pruning, sparsification, and how could it kind of easily be done in practice, and how this sparked another area of research that we will hopefully pursue soon. So these are the base weights, and we would like to reduce the size of them somehow. So we can apply more aggressive quantization into 4 bits, which means that we set part of the bits to 0. And note that we have not saved any space yet, because we still need to store the whole numbers somehow, unless we assume some special hardware support. If we then apply pruning and prune half of the weights away completely and set them to 0, like set them completely to 0, the gray numbers, again, still there is no size reduction because we still need to somehow store that, unless we have a special format. But that number looks like something that could be very easily compressed. And even right now, you can come up in your mind with a compression scheme that actually encodes those zeros in a very succinct way. And it turns out that if you take a model, apply quantization and pruning on top of it, and then apply a standard compression algorithm like zip, you will actually get easy real size reduction that is sometimes important for distribution of the model. Okay, that was it from me. And if you are interested in LLM inference or have some computational algorithms that you would like to speed up, let me know. Feel free to reach out and contact me. Thank you.